All right, so now we've looked at angular speed, and we looked at the difference between the angular speed and linear speed and how they relate. And if you go through essentially the semester and how we started, and we looked at those kinematic variables, so the speed, the acceleration. So we're seeing that now there are some analogies, and we can now define an angular speed, an angular acceleration. And if you look at the next chapter we went over, which was dynamics, we studied forces, we studied Newton's laws and how an object was set in motion. And a very important topic was inertia. All right. And so when we tried to measure inertia for an object that was moving linearly, um, we used the mass of the object. So the question here would be, so if we had mass, again, um, mass to describe linear motion, what would be the analogy here for rotational motion? What should we use? And so that's what we're going to go over in this video. And as it turns out, we have something that we're going to call rotational inertia. So rotational inertia is going to carry the same idea that we used for linear motion. But now we're going to look at the property of an object to resist changes, but now in its rotational state of motion. And that's something we're going to call inertia. It turns out, so this is a rotational inertia. It's going to have a symbol capital I. And we're going to see that it's going to carry some information about the mass of the object, but it's going to be more complex. So the idea is, just like we saw when we studied Newton's first law, that if you look at an object in rotation, so now we're going to have to study, uh, describe the rotation with respect to an axis. Okay, so if I take my pencil, for example, here, if I was to tell you that this is an object in rotation, if I don't tell you the axis, you would have a hard time actually figuring out how to set the rotation up. So if we could have an axis through the center, we could have an axis through the middle here, so we could do something like this. And so when you look at the rotation about an axis that's going to be defined, it's going to tend to rotate in the same way, about the same axis at the same speed, unless something happens, unless you have an external force acting on it. But we'll have to also look at the equivalent of force. So that will be coming up in an upcoming video. So as it turns out, force once again is not going to be enough here. For inertia, we're going to use rotational inertia. And so we had an idea that, so we get the idea that mass is going to be important, but that's not going to be enough in this case. So this rotational inertia is going to depend on two things. One is the mass. So if you increase the mass, you're going to have greater rotational inertia. But it also depends on how you distribute the mass around the axis of rotation. So the greater the distance between the mass of the object and the axis, the greater the rotational inertia. Okay, so this is something that, so you can see that you have some, so if you're the person or the object that is rotating, that means that you have the power to actually change your rotational inertia. So if I'm rotating, if I'm twirling like this around this axis here, all right, so an axis that is going through me, then I can put everything close to the axis, and that will reduce rotational inertia. So if I do this, it's going to make it very easy to rotate, all right? You can try that on if you have a swiveling chair. Now, if I want to increase rotational inertia, all I have to do is increase the distance between the mass and the axis of rotation. So what I can do is extend my arms out. If I do this, essentially the mass on my arms and my hands is moving further away from the axis of rotation. And so if you can try this on your chair maybe. So you can start by rotating like this, and it's going to be very easy. And then you can extend, and you'll see that it will change the angular speed. Um, for a more dramatic effect, you can also hold something heavy in your hands and repeat. And so by having the mass move away from the axis of rotation, you're going to see that you will increase rotational inertia. So that is important. And you can see that we have the skater here using just that. Don't worry about this part here. That's something that we'll tackle later when we talk about angular momentum. But you can see that by extending the arms, we have a greater rotational inertia. And that means that you can essentially rotate slower. And as you bring everything in, so you're making yourself kind of smaller, but really what you're doing is bringing all the mass closer to the axis of rotation, you'll see that then you can spin a lot faster. Okay. And we'll see more how this works when we talk about angular momentum. So that's something you can use also for balance. So here, if you look at the picture, we have a tightrope walker. And so I don't know if you've ever seen a tightrope walker at a circus or maybe something like that, but they usually carry a very long pole. So it's not so much that it's necessarily very heavy, but it's distributing the mass as far away as possible. So they're going to be very, very long. That will increase the rotational inertia. Why would you want to increase rotational inertia? You want to be have as much inertia as possible because you do not want to rotate very easily. So if you want to stay balanced, you're going to hold on to that long pole. Another way to do this is that if you're walking along a line, your tendency will be to stretch out your arms, and that's exactly what you're doing. You are increasing your rotational inertia, so you're more balanced. Essentially, you're making it more difficult to rotate around your feet, okay, if you do this. And so that you're not going to fall, okay? So again, greater rotational inertia means that it's going to be harder to change the rotational state, which means that if you're stable like this, you're less likely to start rotating around your feet, okay? Um, so that rotational inertia is going to be very much dependent on the axis of rotation that you're going to choose. So that means that that's something also very different from inertia the way we've seen it before. Because if I were to look at my pencil again, when I go to apply Newton's laws of motion the way we did, all we had to do was put this on the scale, measure the mass, and that was enough information. Now, this object can have different values of its rotational inertia. So it will have one value of the mass, but again, I could use different axes of rotation. Each one will give me a different value of the rotational inertia. Okay, so you have to be very careful not to assume that a given object is going to have one rotational inertia. So it does have one value of its mass. However, rotational inertia is going to depend on where you place the axis of rotation. So for example, I could have one over to the side. I could rotate it from the middle. I could rotate it like this. And this will all give me different values. And you can see that, for example, if I did this rotation, all of the mass is very close to the axis of rotation. So that would be very low rotational inertia. If I do something like this, and I rotate like around, or you can see better like this, then this will increase the rotational inertia. So it's easier to rotate my pencil around an axis that's passing through it. It's going to be harder to rotate it around an axis that is passing through the center, so something like this. And it's going to be even more hard, even harder to rotate it around an axis, passing through one of the ends. All right, so if to do something like this. And that's because now I've increased the distance from the axis of rotation even more. So there are ways to calculate the rotational inertia for different shapes of different objects. We're not going to bother at all about how we calculate them because that actually requires a lot of math. However, we can look up in our little table what that is expected to be. So if I have my pencil, I would look at the shape that would correspond to the shape of my pencil in here. So I could say, okay, it looks like a thin rod. And you can see that you could pick the axis and then you have a formula that will give you the rotational inertia. So you can see that it always depends on the mass, okay? It will depend on then the geometry of the object. So in this case, L here would be the length of the rod. If I were to look at a sphere, you can see that we are considering the radius of the sphere, for example. And be very careful of where this axis is located, because you can see, for example, that between, so this is the same object, but here I have an axis through here and here through one side, and you can see that we get different factors in front. In this case, we divide by 12. In this case, we divide by 3. Okay. And so indeed, you can see that the rotational inertia for this one is going to be greater, even though it's the same object. So you have different values for different objects. And this is going to be interesting because eventually we'll see how you can calculate the kinetic energy, for example. The kinetic energy. So if you think about it, we can do a little bit of an advanced topic here. So if M, now the equivalent is going to be rotational inertia. If V, the equivalent is omega, and so kinetic energy was 1/2 mv squared, then we're going to just do the analogy and it's going to be 1/2 I omega squared. So that's going to be our rotational kinetic energy. That's important because you may remember that, you know, we used conservation of energy before and it used kinetic energy. And you can see that this is not going to use this rotational inertia. So that means that if you look at different objects, so sometimes we look at two objects on the ramp that are rolling down, and depending on the shape, we can kind of predict which one is going to arrive faster at the bottom of the ramp. And that would be so essentially based on the value of the rotational inertia of the object. So how easy it is to change its rotational state. Very much like checking out the mass of an object and its inertia and seeing how easy or difficult it's going to be to change its state of motion. All right, so now that we have rotational inertia, so we have this mass part. Recall from Newton's laws of motion, we also studied forces. So what are we supposed to do now with forces when we're looking at an object in rotation? What is going to be the equivalent or the analogy for force in rotational motion? I'll stay tuned to find out, and we'll talk about that in the next video. Thanks.